All right, section 1.3, define chemistry. Chemistry is the study of the composition of matter and all the changes it undergoes. Define the term matter. It has to have mass and take up space, which is volume. You may be asked to come up with something that's not matter. Look for something that has to do with energy, light, heat, sound, whatever. Anything that's energy is not matter because we can't mass it and we can't measure its volume because it doesn't take up any space because it's not made of atoms. All right, elements on the periodic table, they're arranged according to atomic number. They do go up based on mass for the most part, not always. There's some exceptions. Check out argon, element 18, and potassium, element 19. You would think this would be the lower one and this would be the higher mass, but it's not. They're actually switched. Argon weighs more, and then potassium, which comes after it, weighs less. So mass goes up in general, but not always. There's some glitches. But atomic number always goes up in order, and elements are in certain groups based on their properties. Everybody in group 1 acts pretty much the same because of their valence electrons, which we learned about recently. Atomic number is equal to the number of protons. So if you know an element's got an atomic number of 8, you automatically know it's got 8 protons in the nucleus, and you know it's going to be oxygen, because only oxygen has 8. All right, columns are known as groups. Rows are known as periods. You can remember it this way. We can write the word group as if it were elements in a group or in a column. And then we can use the P and write the word period as if each of these letters were different elements in the same row. Try to do it the other way, it doesn't really work. So groups, the elements, the letters all go in a column, and the letters for the word period can all go in a row. All right, metals are on the left side of the zigzag of the stair step, while nonmetals are on the right. If you think about the periodic table, and I'm just going to draw a rough picture here. There's a D block, there's an S block, a little hydrogen, we'll throw a little helium in here. If you think about the periodic table, the zigzag lines right around here. Aluminum is not a metalloid. Aluminum is a metal. All the rest of these elements are metals. These guys are nonmetals. Along the stair step, we'll actually jump down to that for a second. Along the stair step are the metalloids. These guys share properties of both metals and nonmetals, which is question number 7 here. Know that aluminum does touch the zigzag, but it is not a metalloid. It is a metal. Every other element that touches the zigzag line, like right next to it, silicon and so forth, those guys are all metalloids. Now, what properties do they share? Well, if it's properties of metals, then we're looking at it's shiny or it has luster. We're looking at the fact that we can draw it into thin wires, or it's ductile. It's malleable. We can hit it and it can be shaped or molded or flattened. It can conduct electricity and heat. It can react with acid and make those hydrogen bubbles. Remember, you put the magnesium in the hydrochloric acid. Magnesium beat up poor little hydrogen, took its girl, and magnesium hooked up with the chlorine. And what happened to poor little hydrogen? Well, it got its electron back and it looked at the other hydrogens in the container and said, what should we do? I know, let's form a covalent bond. Let's share our electrons and let's make hydrogen that turns into a gas and leaves the container. And we did this in our big lab. Now, why does all this stuff happen? Well, metals have a sea of electrons, meaning the nucleus and all of the internal electrons, not the valence, but all the rest of the electrons on the inside, they all stay together, but the valence electrons are free to move around. The valence electrons from this guy doesn't necessarily stay with that guy. It might make its way all the way over here and be around this guy for a while. And then maybe a hammer comes down and hits everything, and then this guy shifts and now it's down here. But because these electrons, the valence electrons, are free to kind of just move around and they're not stuck in a rigid position, they can adjust. And then we can take this big thing and force it into a little tiny opening and squish these guys down in there. And the fact that the electrons move allows that to happen. We could hit it with a hammer. We could put a big force on it and make a big indentation in it, and everything will adjust because these electrons are not stuck in one position. Nonmetals, however, they're the opposite. They don't have a sea of electrons. They're rigid, they're stuck in certain spots if they're not a gas. They are dull, they are non-ductile, we can't draw it into a wire, they're brittle, if you hit it, they'll shatter. Think about chalk, very brittle. Poor conductors are non-conductors of heat and electricity, and they don't do anything interesting with acids. They don't produce those hydrogen bubbles. What else we got here? Names for the groups, you should know these by now. Group 1, alkaline metals. Group 2, alkaline earth. Think 1, we've got 1 interesting word. Group 2, we've got 2 interesting words before metal. Group 7 of the halogens, 8 of the noble gases. Group in the D block, basically. These are your transition metals. These guys are the weird elements. These kind of like the rebels of the periodic table. They do weird things. They don't follow the rules. And then down below in the F block, way down below, there's the 2 rows. These are your intertransition metals. We're not going to use those a whole lot, but you know where they are. All right, physical chemical properties. Physical is a property that you can see or measure, and you're never, ever, ever going to change anything about it. There's no chance of you changing anything. And if you were in my class, I talked about pajamas, and I wasn't sure when I bought the pajamas why they fit so tightly around my little kids. And I looked at them and I said, well, are they just small? What's going on? And I realized that those pajamas are flammable, the ones that fit snugly. That's why they have to fit snugly, so the kid can't accidentally brush their arm in the big baggy pajamas into a flame or something if they have a candle around or whatever. So the observations that I could make where there's no chance of me changing anything, I don't know, maybe I could look at the size, I could look at the color, I could look at the mass, I could look at the volume, how much space they take up, I could measure the density. If I get the volume and the mass, I can divide the two and get the density. I could do all sorts of stuff with those pajamas as long as I don't ever change anything. But if I want to find out if they're flammable or not, then I'm going to test it. I'm going to take the PJs and I'm going to bring a match near it and I'm going to see if they catch on fire. So I could possibly change it. I could change the chemical structure by testing it. It may or may not catch on fire, but if it does catch on fire, I don't have pajamas anymore. I have a bunch of ash and some gases that were given off. So if you're thinking, how can I find out whether or not something has this particular property, and you test it and you know if you test it you might change something, then it's automatically a chemical property. Physical and chemical changes. If it's physical, it may look different. Like you think about liquid water, H2O in the liquid phase versus H2O in the gaseous phase. Like look around in the room right now. There's water vapor in the air. In the summer, when it's humid, there's a little bit more water vapor in the air, but you don't see it. It looks different than regular liquid water or than solid water like ice. It looks different, but it's still got the same chemical structure. Water is always like this. 1 oxygen, 2 hydrogen. It's always, always, always like that, whether it's a solid, a liquid, or a gas. So it looks different, but it's still the same thing. So we could go through phase changes. We could melt the solid. We could boil the liquid. We can condense the gas back to a liquid. We could freeze the liquid back to a solid. It's still H2O. It might have more or less energy. It might move faster or slower, but it's still H2O. That's physical, and think physical phase change. Chemical is a change that's going to produce something new. Bonds are going to be broken. We're going to end up with something brand new. And these are our chemical reactions. Chemical change, chemical reaction, same thing. They're synonyms. You should think about the lead article that you read. I'll give you a major hint here. The biggest problem with lead poisoning is that you can't undo the damage that's already been done. If a little kid has been exposed to high levels of lead, they've been contaminated, and it doesn't take much. You could just have a few grains of dust, and it could end up contaminating an entire house. And it's not just from eating paint chips. You could be sanding floors. You could be running your hand along a windowsill, and the wood that has a lead paint on it or the lead in it, that'll get up into the air or on kids' hands or whatever. It's not little kids always just eating chips of paint. But long story short, if a little kid does end up with high levels of lead in their blood, then it could do some brain damage, and that could be a lifelong consequence of having high levels of lead in your house. So lead's a major issue. You got to get your houses tested for lead if they were built when people still use lead paint, which was a long time ago. It's since been outlawed. All right, put a circle around the reactants. Reactants are what you start with. We run the reaction with these things. It's like your ingredients, and this is what we produce. Products are on the product side or on the production side, just like a math equation. You start with these things, put them in, you get those things out. Now, according to the law of conservation of mass or matter, as long as we're not dealing with nuclear chemistry, whatever we start with has to equal what we end with. So if we add these two things up, it should equal the sum of these two things. So if we don't know what one of those missing parts is, add this up, get your total, so we know that this equals 96.3, and we know this side's 95.3 plus x. What's 95.3 from 96.3? 1.0. So that means our x is 1.0. So we now know that if we start with these two different substances, we're going to end up with these two different substances. And we can predict, assuming we have 0% error, assuming everything goes perfect in a reaction, that's what we should get. That's our accepted value. And then we run reactions and we see, did we get that? Usually not. All right, finally, 5 signs of a chemical reaction. If we see gas, if we see a big change in temp, it could go up, it could go down. If we make a precipitate, remember a precipitate is a solid that forms when we have two liquids mixing. If we see light or sound or some sort of change in color. But the biggest thing you're looking for is there a new chemical? Is there a new chemical formula? Are there new bonds being made or broken? That's the biggest sign of a chemical reaction.